This lesson is about reduction of order. Let's suppose that we want to solve a second order linear homogeneous differential equation that looks like this: a2 of x y double prime plus a1 of x y prime plus a0 of x y equals 0. In order to get the general solution to this differential equation, we need two linearly independent solutions, y1 and y2. We'll talk a little bit more about how to check for linear independence in class. And then once we get those two linearly independent solutions, we can form the general solution as y equals a constant c1 times y1 plus a constant c2 times y2. What we're going to learn today is a method called reduction of order. Reduction of order is a method that we can use for constructing a second solution y2 given a known solution y1. So it can only be used if you know a solution and you want to construct a second solution based on that known solution. But it's actually going to be really useful to us. So let's start out with an example of how reduction of order works. And what we're going to do is we're going to find the general solution to this differential equation, y double prime minus 2y prime plus y equals 0. And we're going to do that by first, and this is kind of dropping out of the sky here, but let's just verify that a known solution is y1 equals e to the x. And so we can just check this by plugging in y1 and its derivatives into the original differential equation. But the purpose of this is actually to, once we're given the solution, be able to construct a second solution. So if we get the derivatives of y1 prime is e to the x, and y1 double prime is also e to the x. So we plug these derivatives back into the original differential equation. We're going to get y1 double prime e to the x minus 2 times y1 prime, which is e to the x, plus y1, which is e to the x. And all the terms on the left-hand side will equal to 0. So y1 is actually a solution. But the main point is that if you're given the solution, can we construct a second solution is the goal of this technique of reduction of order. So let's go ahead and use y1 now, and I'll show you how to use it to construct a second solution that will end up being linearly independent. So let me just erase this, and I'm going to rewrite that differential equation. So we're still trying to find the general solution to y double prime minus 2y prime plus y equals 0. And we know that y1 equals e to the x is a solution. So reduction of order involves constructing the second solution y2 by assuming it is the first solution y1 of x times some unknown function u of x. And what we're going to do is we're going to take the derivatives of y2 and plug them into the differential equation. And we're going to use the differential equation to try to solve for u of x. If we can figure out what u of x is, we already know what y1 is. So then we have generated another solution, y2. So the goal is we want to solve for u of x by substituting y2 and its derivatives into the differential equation. Okay, so let's go ahead and do that. So y2 actually equals y1 times u. And we know what y1 is. We know the solution is e to the x. So y2 actually equals e to the x times u. U is the thing that we don't know and we're trying to solve for. So let's go ahead and take the derivatives of y2. And we'll substitute those derivatives into the original differential equation in an attempt to solve for u. So the derivatives, y2 prime, and I have to use a product rule because e to the x is a function of x, and u is also, it's an unknown function of x. So the product rule gives the derivative of the first term, e to the x, let me just write it out, derivative with respect to x of e to the x times u, plus the first function, e to the x, times the derivative with respect to x of the second function. So that ends up being the derivative of e to the x is e to the x times u plus e to the x, and I'm going to just write the derivative with respect to x of u as u prime. And then I need to take one more derivative, so I can substitute y2 into the differential equation. And if I differentiate, I'm going to have to use the product rule again. I'm going to use the product rule on the term e to the x times u. The derivative of the first is e to the x times the second u, plus the first function e to the x times the derivative of the second function u prime. So that's the product rule applied to the first term here, plus, now I apply the product rule to the second term. The derivative of the first function is e to the x times the second function, which is u prime, plus the first function e to the x times the derivative of the second function. So the derivative of u prime is going to be u double prime. So the second derivative looks like e to the x u plus, I actually have two terms that are e to the x u prime, 2 e to the x u prime plus e to the x times u double prime. Now I can substitute y and its derivatives into the dE to try to solve for u. y2 prime, y2 double prime into the differential equation. And so I'm going to get something like y2 double prime minus 2y2 prime plus y2 equals 0. y2 double prime was e to the x times u plus 2 e to the x u prime plus e to the x u double prime. That's going to be minus 2 times y2 prime. y2 prime is here. It's e to the x u plus e to the x u prime. And then the last term is plus y2. And y2 is just e to the x times u. And that should all equal 0. And so now we're going to we have another differential equation that involves the function u. And we're going to try and solve this differential equation for u. Actually, something really nice is going to happen next. So let me erase everything but leave that last line. And what I want to do next is I want to collect my terms that involve u double prime and the terms that involve u prime. So u double prime times, that is, actually I can simplify before I do that. If I divide every term on the left side, it has an e to the x in it. So I can divide the entire equation through by e to the x and get rid of all these e to the x's. The only term that involves u double prime is this one. So I get a u double prime. Next I'm going to collect my terms that involve u prime. So the terms that involved u prime were this term, and that has a coefficient of 2. This term, that has a negative 2. And then those are the only terms that involved u prime. Next, I'm going to collect my terms that involve u. So this first term has a coefficient of 1. This term has a coefficient of a negative 2 when I distribute. And the last term has a coefficient of 1. This should all equal 0. Notice that I end up with just u double prime. This is going to be 0. This, excuse me, is also 0. So the only thing I end up with is u double prime equals 0. So what I can do is integrate both sides with respect to x. Remember, u is a function of x, to try to find u. So I get u prime equals the integral of 0 dx is just some sort of constant. Let's call it c1. Now I can integrate one more time to find u. And so I get u is equal to c1 times x plus another constant, c2. So this actually, now I have found my second solution, because remember y2 was actually y1 times u, and y1 was the known solution e to the x, and u is this solution c1x plus c2. And since we just need something for u, what we can do is choose c1 to be 1, and choose c2 equal to 0, and that's going to make this much simpler looking. y2 equals e to the x C1 is 1 and C2 is 0, so it's just e to the x times x. And that's going to be our second solution that we constructed based on the known solution e to the x. So we now can form the general solution. The general solution is going to be y equals c1 y1 plus c2 y2. And so this equals c1 e to the x plus c2 times x e to the x, and that's going to be the general solution to our differential equation. So and we've solved our first second order differential equation.